Okay, I think we're recording again. Okay, so let's look at this example. This is example 4.4 in your book. Don't try this at home. Now, so let me read the problem since y'all can't read it, or you could, but not in real time. This is asynchronous type education. Don't try this at home. A stuntman drives a car off a 10.0 meter high cliff at a speed of 20 meters per second. I think that's about 45 miles per hour. How far does the car land from the base of the cliff? And it doesn't have to be a car. It could be you on a bicycle. It could be you on a sled going off a cliff. Now, that's more probable, but 10 meters high, that's 33 feet. I wouldn't recommend that. Unless the snow would need to be really, really deep. I'm talking about multiple feet deep to land safely. So, how far does the car land from the base of the cliff? You could roll a ball this way. Yeah, that's it. Because if you do a car, and he's going off, he's going to hit, and he's going to land over. Not like the book. He's not going to be horizontal. You know, walk like Egyptian horizontal. He's going to be nose heavy in the front. The car's going to want to tip over. It's going to tip down, rotation about center of gravity, all that stuff that you will learn about. And so he hits here, there's a bunch of gas in the back, catches fire, and everybody dies in the car. But there was nobody, it was a stunt car and everything like that. It really wasn't a stunt man, it was really a stunt, stunt double. It was a double for a stunt double. So it's a stunt double squared in there. It's one of those, guys you would see, the test dummies. So this is a dummy stunt double. DSD. Alright, so we got rid of that part of it. So we're going here. I drew a picture. I labeled it. Let's list some knowns and unknowns. So you know the initial velocity, and that's in the x direction only. We're going to have to look at everything in x and everything in y. Whoops. X and y. We're going to look at that. And then we're going to list our knowns for x and y. So this initial velocity in x is 20 meters per second. Let's put our coordinate system right here. Right where the car is at, or base will be right here. So this will be 0, 0 right here. And so, if that's true, the initial position in x is 0. So just go straight up. He's at the starting point. Makes life easier. Try to draw your coordinate system. You can put it at the top, put it at the bottom. Doesn't matter. Nature doesn't care where you put your coordinate system. What's the acceleration in x? Is anything making it go faster in x once he leaves the cliff? No, because the car's wheels were the only thing moving it faster in x. And there's no air resistance in this problem, which you can neglect as long as it's not, too much, and not in the air for too long. So the acceleration x is 0. And x final position is A. That's what we want to know, how far he goes away from the cliff. This is sometimes known as the range. Not something you cook on, but the range of how far it went out. All right? If you're shooting and you say, this thing I can hit a target at 800 meters, so the range of this gun, maximum range where you can legitimately hit a target, is 800 meters. If you can't legitimately hit a target outside of that, for me shooting, it's not the gun that's limiting the range, it's my ability to shoot. So I shoot my range is much shorter than most guns' range, the way I shoot. All right. So y position, we're going to say it's way up here. So y initial equals 10.0 meters. Y final is 0 meters. And I'm going to move this up here because I'm running out of room. The initial velocity in y, it's not moving it all up or down initially. As it falls, it gets some y motion. But initially it doesn't in y. The final in y we don't know. We may not need it. Maybe we will, maybe we won't. We'll have to see. And acceleration in y is negative 9.80 meters per second squared. So that's gravity. It's pulling it down. And I said y initial. Okay. Oh, the y final is 0. I think that's it. I hope so, or I have to go re-record this. Right? Re-record it. Huh. List our knowns, list our unknowns, draw our coordinate system. Now let's think of relevant equations. But what you need to do when you're solving these problems is think of motion only in x and only in y. Kick something out of the way there. All right. Now, so there's lots of ways of doing this. You'll see different ones relevant to however you, the book you look up at, the text you look at, the workshop, whether it's Khan Academy, whatever. What I'm going to show you has worked for students that it seems to work, and I've developed it over time. And somebody showed me this, and I probably stole it or modified it from them. All right? So I'm a physics thief, educational thief, you could say. So what I will do is, I will basically deal with x motion here on this side of the chart and y motion here on that side of the chart. And I will remember that the time in x equals the time in y. Now if I set it up like this helps me think, separate my thoughts so I can only think in x and only think in y. Because projectile motion, because it's a vector, we can break x and y motions down, and that will give nice curved motions. But we can break down in this x motion only and y motion only, because they're independent of each other. Okay? All right. So let's think of this. So let's just think of x and think of y. So in x, we know velocity, initial position, final position we don't know, acceleration, don't know the time. Do we have any equation that relates all of them? Oh, by the way, time I'm going to put here. We don't know that. I about forgot that one. You must forget something. Let's just use our basic big long equation. X final, X final equals x initial plus initial velocity times time plus 1/2 acceleration times initial velocity times the time. AT squared. All right. Now, if I use that one, acceleration is 0, so that goes away. Woohoo! That's more that little short one, right? So I know the initial velocity in x. I know the initial position in x. I don't know the time, and that's what I want to find. And I don't know it. So if I can find the time, I can come back into here, plug this back into this equation, and get the answer, because it's got what I want right there. That's what I'm looking for. Now some of you might be thinking, why didn't you use v final squared equals v initial squared plus 2a delta x? Well, if you put that one up here, acceleration is 0, so I just got v final squared equals v initial squared. Square root both sides. V final is v initial. Doesn't tell us anything. We can get information we want, but that's what we want to know. All right. Can't do anything else in x. So let's move over here to y. See if we can find the time that it moves in y. And then plug that back in over here in x. Darn these multi-step problems, nature. But that's the way the universe works. All right. So what do we know? Well, we know acceleration. We know the initial velocity is 0. Final velocity we don't know. We don't know the time. Can we find the time? Let's see. Could we use this equation here? So I'm going to put this in black. So y final equals y initial plus initial velocity in y plus 1/2 a t squared. Initial velocity in y times the time plus, I had to put a time in there, so it's initial velocity in y times the time plus 1/2 at squared. So let's think about it. Y final, we know. Y initial, we know. The initial velocity in y is 0. We know that one. Geez, that term goes away then. Woohoo! The acceleration in y, well, that's in y, we know. Wait a minute, I've got an equation now that my only variable is the time. And that's what I want to know. So if I can find the time here, I can plug it back in over there. So let's do that. Okay, y final is 0. Y initial is 10.0 meters plus 1/2 acceleration is minus 9.80 meters per second squared times time squared. I'll move this to the other side. I'll take half of that. And I'll get minus 10.0 meters equals minus half of 9.8 is 4.90 meters per second squared times the time squared. All right, so I got what I want here. Let's get it by itself. This is algebra now. So move this to the other side. So divide both sides by negative 4.90 meters per second squared. That cancels. So that's with time squared equals 4.9 in the negatives cancel. Negative or negative is just positive. 4.9 into 10, that's about 2.1. Let's see if the book has it. I don't have a calculator with me. That's about 4.1 though, I'll tell you that. So we'll just say, I'm going to say approximately not 4.1, 2.1. Now, what happens, I got to cancel this, that's meters over meters per second. The meters cancel, the second goes up top over second squared. Well, now I got to square root both sides. That squared, get t by itself. And the square root of 2, I know is 1.414 because my Miss Swink and, 10th grade drilled that in our heads. We had to know it. All right, so 2.1 is a little bit bigger than that. The book says 1.43, so that makes sense. That's reasonable. Remember that reasonable's check on our answers. 1.43 second, square root of second squared is a second. Remember, the square root of anything to the second power is just that. Because remember, this is really equal to the 1/2 power if you do the square root. And what do you do here, math? Remember, power to a power, multiply exponents. So that's 2 over 2, just 1. Okay? You got to remember those little math thingies. I know they seem trivial and you try to forget them, but you need them. Okay? It actually had a use. So we know what the time is. Now, I didn't put time in y because the time in x equals the time in y. But that means then, we know that's true. So whatever I have here, I can stick them right there. So let's do that. So x final, x initial is 0. And the initial velocity is 20 meters per second, and the time is 1.43 seconds. So that means x final, 20 times 1.43, what is that, 28.6? Woohoo! And the seconds cancel, that's a second over 1. So 28.6 meters per second times seconds over 1, the seconds cancel, 28.6 meters. We know how far away he lands from the cliff. But it's not a he, it's anthropomorphic. It's the dummy stunt double So we don't want to hurt anybody, of course. And so it lands that far and dies of, well, it didn't die very differently, was alive. Okay. So that's how you do projectile motion problems. Horizontal, no launch angle. Next video, or I'm going to try to splice these together. We'll see, right? The next one will be at an angle. And let's see what happens.